Hi. In this part of the lecture, we're going to talk about how to fit a matrix factorization model. So let's remind ourselves what a matrix factorization model is. So remember we talked how we had a utility matrix. So what was a utility matrix? Utility matrix was a matrix that had the ratings that a user had for a particular item. So for example, here in this row, we have the ratings of user 1. And maybe down here we have the ratings of user I. And maybe over here you have the ratings given to item J. Okay. And we define Yij to be the rating given by user I to item J. Remember that most of this matrix is actually empty. So we have some ratings, maybe 1% of the matrix is going to be non-empty. And these are going to be these Yij's that are going to be actual ratings. For now, let's think about ratings as numbers maybe from 1 to 5. This could change. This could be different as well. So this is my matrix. So we're going to call this matrix Y. So let's call it Y. This is metric and the elements of Y's are Yij's. So the matrix factorization models makes the assumption that this matrix can be approximated by the multiplication of two matrices. This one we're going to call U, and this one here we're going to call V transpose. And in general, this matrix, the way to think about these matrices is that they are very skinny. So these, if we had, for example, in this case, we had in U users, and we had in M items, then our utility matrix would be NU times NM. The matrix U is going to be NU times K, where K is a number. For example, K could be 50 or 100, but NU may be millions, and NM also could be millions of items or millions of users, right? So the way to think about these matrices is that they are like kind of skinny. So you are trying to kind of, this is in a way a method of dimensionality reduction, basically. But since most of this matrix is empty, we are trying to approximate something that is almost kind of empty by this multiplication of two matrices that have, in which we basically are assuming that they have a much simpler structure, let's say. Okay, so the prediction, so the goal of this matrix factorization problem is predicting Yij hat, which is the prediction that our model is given to the rating that the user I is going to give to item J. Okay, so, and as we talk about, so the model is our model is going to be something like this. It's going to be the dot product between Ui times Vj. So what is Ui? Ui is a vector of dimension k that is here, and is a representation of user I. It's a k-dimensional vector, maybe a 100-dimensional vector that represents our user I. Okay, and Vj is maybe it's here, is a vector that represents our item J. Okay, and our simple model that we are considering right now, the matrix factorization model, is going to is basically saying that the rating that I'm giving to that user I is given to item J is going to be a dot product between these two vectors. Okay, so So basically, before we talk about anything else, let's talk about what are the parameters of this model. Well, the parameters of these models are all of the representations UI of users and all of the representations of VJ of items. So we are going to learn together the representation of users and item through an optimization process. Okay, so basically the matrix U and the matrix V are going to be our parameters. So how many parameters do we have? Let's count. So U is NU times K plus V is NM times K. So this is the number of parameters we have. Okay, so before we can say anything about how we're going to fit this this model, we have to define some kind of loss function or cost function. So you have seen that in logistic regression or linear regression, that in order to optimize to find the parameters of the model, the first thing you do is that you define some kind of loss function. And similarly to regression, we're going to use the square loss function in this case. So let's talk about that for a sec. So here we are going to define Yij minus Yij hat square, right? This is the same as Yij times minus Ui times Vj, right, square. And so we have to like sum over our training data, right? So what is our training data? Our training data in this case are all the ratings that we have, or maybe a subset of them. Maybe we will take like 80% or 90% of the ratings we have, and we're going to basically use them for our training, right? So we have to sum over Iij in our training data. And the Iij better have some kind of rating, right? So let's define our Ij to be 1 if Yij is not empty. Meaning if Yij actually is a rating that exists in our training data, right? And 0 otherwise. So what we're going to do is that we're going to sum over I comma j such that Rij is equal to 1. Okay, so this is going to be and then we're going to divide by n, where n is the number of ratings that we have. Okay, so this is our loss function. Okay, now this loss function is a function of UI and VJ, right? You remember we have all of these parameters that we want to learn. So let's define, so basically we're going to call this E of U and V, which again, this is 1 over n, the sum over I comma j such that Rij is equal to 1, and this is like Yij minus Ui times Vj squared. Okay, so now a question for you guys, and let me actually make sure my U's and my V's are a bit different. So a question for you guys, so what is the simplest method that we can use to fit this model? Well, the simplest method is gradient descent. So if you remember in gradient descent, what do? So if we had, say, a cost function E of W, right? How do we update W? We say, well, W is gonna be W minus dE dW, and then we're gonna multiply this by a small number called the limit rate. Okay, so this is gradient descent. So let's try to figure out what are the equations for gradient descent for this particular problem. In this part of the lecture, I will derive the equations, and then I'm gonna have a second lecture in which I am going to vectorize the equations, and that's gonna be very important for your homework, because in your homework you're gonna wanna use the vectorized equations. Okay, so before we get into that, let's remind ourselves of a few of the possible properties of derivatives. Okay, so for example, suppose you have a function f of x plus g of x, and you want to take the derivative of that. Well, that is just f prime of x plus g prime of x. Notice that when I say prime, this is the same as if I have df, if I'm trying to differentiate this with respect to x, it will be df dx plus dg dx. Similarly, suppose that I have something like this. I have f of g of x, okay, and I want to differentiate this with respect to x. So let's say dx. So this is df in g of x dx times dg dx. Okay, so these are pretty much the most important properties that we need to remind ourselves of, and yeah, so we're going to be using that. So let's let me actually show you an example that may be useful here. Suppose you have this function and I want to differentiate this with respect to x. Okay, notice that the square, see, I'm composing different functions here, and one is the square, right? So I can differentiate with respect to the function square, and then differentiate the inside of that with respect to x, right? That's basically what this function here is saying. So the function f here is x squared. Okay, so that would be 2x, right? So that's basically what I'm talking about. So I'm going to have a 2. I'm going to have y minus f of x. That's the derivative of this part with respect to 2x. And then I am going to take this part inside here and differentiate it with respect to x. But there is a y which doesn't depend on x. It's not a function of x, it's a fixed number. Then minus f of x. And what's the derivative of minus f of x with respect to x? There is the minus here, and then there is the f dx or f prime, right, of x. Okay, I think this is gonna be useful for you guys later on. So this is an example. So so remember the two. So we have our function e of u v. So we have that, and what are the derivatives we are actually interested in? So we are interested in dE duik, and we are also interested in dE dvjk. So these are two kind of numbers actually, right? So we have the vectors ui and vj, and uik is one of the dimensions of that vector ui. Vjk is one of the dimensions of those vectors, right? So those are the derivatives that we're going to need to be able to compute the gradient descent equations. Okay, so before I before I do something more sophisticated, let me consider, so I have this, my y hat ij is this ui times vj, and remember that this is a dot product, so basically this is the sum over s of uis times vjs, right? This is a dot product between the vectors ui and the vectors vj. So I think before looking at anything else, I would like to find the derivative of y hat ij with respect to ui prime, and this I prime is a different user than I. So there is a user I and then the user I prime, right? User I prime may be k, dimension k, okay? So, and basically what I would like you guys to see, and I'm gonna discuss this later, is that this here is either 0 or vjk. This is 0 if I and I prime are not the same, and this is vjk if I is equal to I prime. Let me show you this with an example, because I think an example makes more sense. Okay, so suppose that I have the following formula. So I have the formula u11 times v31 plus u32 times v22, okay? And I want to differentiate this with respect to u31. Well, this is 0 because u31 is not in this sum here. So the variable u11 is a different variable than the variable u31. The variable u32 is a different variable than the variable u31. Okay, so the variable u31 is the first dimension of the user 3. Okay, so and this is a variable that is independent to the other ones. So this is 0. Now if I have something more like this old formula, like u31 v31 plus u32 v22 so basically if you see this, then this is v31 is the derivative with respect to u31, Why? Because this part here, again, doesn't depend on u31, right? This is the part that depends on u31 and is multiplying, this u3v1 is multiplying by v31, and so then we know that the derivative here is v31, okay? So by looking at this, hopefully it's clear now to you guys that basically when we derivate y hat ij with respect to u I prime k, first of all, if I prime is not equal to I, u I prime k is not in the sum at all. So everything is 0. And if I is equal to I prime, the only interesting part that we have is the part that is u I prime k times vjk. That's the only part that is actually non-zero, the derivative is non-zero, and the derivative is vjk, okay? If this is something that is difficult for you, try to slowly see this and ask me any questions on office hours, okay? Okay, so this is an important part that we need. Now let's look at yij minus ui times vj squared. The derivative of that with respect to u I prime k. Okay, so we kind of already know how to differentiate part of this. So this is gonna be, if you remember, this is 2 times yij minus ui times vj, and then there is a minus, and then there is dui vj dui prime k. And if you remember from what we talked about before, this is equal to 0 if I is not equal to I prime, and this is equal to minus 2 yij minus ui times vj, and then what do we have in here is v we have vj k. This is when I is equal, so equal j. Okay, so now if you remember, like, what we are actually interested in is to derivate the sum with respect to I comma j such that rij is equal to 1 of this. So we want to find the derivative of all of this with respect to u I prime k, okay? And this is a 1 over n here that I'm gonna just put down here. So notice that if I and I prime are not the same, the derivative of this internal sum is actually 0, right? So I'm claiming that I'm not gonna be able to sum over I anymore, because everything that is not I prime is gonna be 0. So I'm gonna sum over j for r I prime j equal to 1, and then we're gonna have y I prime j. Remember, everything that is not I prime is just gonna be equal to 0, so u I prime times vj. So, and we had a 2 over here, and we had a minus, if you remember, and then here we had vjk. Okay, so finally, if we think about the formula yik, notice that I'm putting I instead of I prime here. This is yik plus, because we have minus the learning rate times the derivative, so the learning rate, and then we're gonna have 2 over n, the sum j equal r ij equal to 1 of y ij minus ui times vjk. Okay, so guys, I'm gonna stop here, and I will encourage you to, now that you have seen this part, you should go ahead and try to derive the equation with respect to so basically the equation for vjk. So what is the equation? What are you gonna write here? Okay, see you in the next video.